Morning, Gophers. We are all on the path to Go To together, but none of us exactly know where that path leads, or sometimes even what direction the path goes. Today I want to talk about how we actually find and follow the path to Go To. Here's what the process looks like. We experiment with Go as it exists now to understand it better. We learn what works well and what doesn't. And then we experiment with possible changes, learning what works well about them and what doesn't. And based on what we learn from those experiments, we simplify, and then we experiment again, and then we simplify again, and so on and so on. During this process, there are four main ways we can simplify the overall experience of writing Go programs: reshaping, redefining, removing, and restricting. The first way we simplify is by reshaping what exists into a new form, one that ends up being simpler overall. Every Go program we write serves as an experiment to test Go itself. In the early days of Go, we quickly learned that it was common to write code like this add to list function, and we'd write the same code for other kinds of slices. Our programs were too complex because Go was too simple. So we took the many functions like this and reshaped them into one function provided by Go. Adding append made Go a little more complex, but on balance, it made writing Go programs simpler, even including the cost of learning about append. So here's another example. For Go 1, we looked at the very many development tools in the Go distribution, and we reshaped them into one command. The Go command is so central now that it's easy to forget we went so long without it. We added code and complexity to the Go distribution, but on balance, we simplified the experience of writing Go programs. The new structure also let us do new experiments. A second way we simplify is by redefining functionality we already have, allowing it to do more. Like simplifying by reshaping, simplifying by redefining makes programs simpler to write, but now with nothing new to learn. For example, append was originally defined to read only from byte slices, or from slices. And so when appending to a byte slice, you could append bytes from another byte slice, but not the bytes from a string. And we redefined append to allow reading from a string without adding anything new. A third way we simplify is by removing something when it has turned out to be less useful than we expected. Removing means one less thing to learn, one less thing to fix bugs in, and one less thing to be distracted by or use incorrectly. Of course, removing also forces users to update their programs, maybe making them more complex. But the overall result can still be that the process of writing Go programs becomes simpler. And finally, we can simplify by restricting what is allowed. From day one, Go has restricted the encoding of source files. They must be UTF-8. This restriction makes every program that reads Go source files simpler. They don't have to worry about encodings in Latin 1 or UTF-16 or UTF-7 or anything else. Another important restriction is gophumped for program formatting. Nothing rejects Go code that isn't formatted with gophumped, but we've established a convention that tools that rewrite Go programs leave them in gophumped form. If you keep your programs in gophumped form too, then these rewriters don't make any formatting changes. When you compare before and after, the diffs you see are real changes. This restriction has simplified program rewriters and led to other successful experiments like Go imports and Go rename. So this is a good model for what we've been doing the past 10 years, but it has a problem. It's too simple. We can't just experiment and simplify. We have to ship the result. We have to make it available to use. Of course, using it enables more experiments and possibly more simplifying, and the process cycles on and on. We shipped Go to all of you for the first time on November 10th, 2009. And then together, we shipped Go 1 in March 2011. And we've shipped 12 Go releases since then. All of these were important milestones. They enabled more experimentation and helped us learn more about Go, and of course, made Go available for production use. When we shipped Go 1, we shifted to focus explicitly on using Go to understand this version of the language much better before trying any more simplifications, especially big ones. We needed to take time to experiment, to really understand what works and what doesn't. Of course, we've still had 12 releases since then, but we've been focusing on ways to simplify Go development without significant language changes and without breaking existing Go programs. For example, Go 1.5 shipped the first concurrent garbage collector, and then the following releases improved it. That simplified Go development by removing pause times as an ongoing concern. At GopherCon in 2017, we announced that after 5 years of experimentation, it was time to think about significant changes that would simplify Go development again. Our path to Go 2 is really the same as the path to Go 1, experiment and simplify and ship, towards an overall goal of simplifying Go development. For Go 2, the concrete topics that we believed were most important to address are error handling, generics, and dependencies. Since then, we realized that another important topic is developer tooling. I'm going to spend the rest of the talk showing you how our work in these areas follows that path. And along the way, we'll take one detour to inspect the details of what will be shipping soon in Go 1.13 for error handling. Now, it's hard enough to write a program that works the right way in all cases when all the inputs are valid and correct, and nothing the program depends on is failing. When you add errors into the mix, writing a program that works the right way no matter what goes wrong is even harder. So as part of thinking about Go 2, we want to understand better whether Go can help make that job any simpler. There are two different aspects that could potentially be simplified: error values and error syntax. We'll look at each in turn with the technical detour I promised, focusing on the value changes in Go 1.13. Error values had to start somewhere. Here's the read function from the first version of the OS package. There was no file type yet, and also no error type. Read and the other functions in the package returned erno int64 directly from the system call. This code was checked in on September 10th, 2008 at 12:14 p.m. And like everything back then, it was an experiment, and things changed quickly. 2 hours and 5 minutes later, we had a new API. The new API introduced the first error type. An error held a string that could return the string and also print it a standard error. The intent here was to generalize beyond int64s. We knew from past experience that error numbers were too limited, and that it would simplify programs not to have to shoehorn all the detail about an error into 64 bits. Using error strings had worked reasonably well for us in the past, and so we did the same here. This API lasted 7 months. The next April, after more experience using interfaces, we decided to generalize further and allow user-defined error implementations by making error itself an interface. We simplified by removing the print method. And then for Go 1 2 years later, based on a suggestion by Roger Pepe, os.error became the built-in error type, and the string method was renamed to error. And nothing has changed since then. But we have written many Go programs, and as a result, we have experimented a lot with how best to implement and use errors. Making error a simple interface and allowing many different implementations means we have the entire Go language at our disposal to define and inspect errors. We like to say that errors are values, the same as any other Go value. Here's an example. On Unix, an attempt to dial a network connection ends up using the connect system call. That system call returns a syscall.erno, which is a named integer type that represents an error number and implements the error interface. The syscall package also defines named constants. In this case, econrefused is number 61. And code that gets an error from a function can test whether the error is econrefused by using a simple value equality check. Moving up a level, in package OS, any system call failure is reported using a larger error structure that records what operation was attempted in addition to the error. There are a handful of these structures, and this one, syscall error, describes an error invoking a specific system call, but with no information about its arguments. Moving up another level, in package net, any network failure is reported using an even larger error structure that records the details of the surrounding network operation, like dial or listen, and the addresses involved. Putting these together, the errors returned by operations like net.dial are not just strings. They have real structure. In this case, the error is a net.op error, which adds context to an os.syscall error, which adds context to a syscall.errno. Because errors are values, the entire Go language is available to inspect them. Here's an example from package.net. It turns out that when you attempt a socket connection, most of the time you get connected or you get connection refused, but sometimes you can get a spurious EADDER not avail for no good reason. Go shields user programs from this failure mode by retrying. And to do this, it has to inspect the error structure to find out whether the syscall.errno deep inside is EADDER not avail. So here's the code. A type guard peels away any net.op error wrapping, and then another one peels away any os.syscall error wrapping, and then finally we check the error for equality with EADDER not avail. What we've learned from years of experience from experimenting with Go errors is that it's very powerful to be able to define arbitrary implementations of the error interface, to have the full Go language available, both to construct and deconstruct errors, and not require the use of any single implementation. This property that errors are values, and also that there is not one required error implementation, is important to preserve. But not mandating one error implementation enabled everyone to experiment with additional functionality that an error might provide, leading to these packages and many others. But one problem with this is that as a client, you have to program to the union of all the possibilities in your program. So a simplification that seemed worth exploring for Go 2 was to define a standard version of common, agreed-upon optional interfaces so that different implementations could interoperate. The most common added functionality in these packages is some method that can be called to remove context from an error, returning the error inside. Packages use different names and meanings for this operation. Sometimes it removes one level of context, and sometimes it removes all of them. For Go 1.13, we've introduced a convention that an error implementation adding context to an error should implement an unwrap method that returns the original error, unwrapping the context. If there is no inner error, either it shouldn't have an unwrap method, or the unwrap method should return nil. And every error wrapping type in the standard library that had an exported error field still has that field, but now also has an unwrap method returning it. And the way to call this method is to invoke the helper function errors.unwrap, which handles cases like error being nil or not having an unwrap method at all. And so we can use the unwrap method and the unwrap helper function to write a simpler, more general, spurious not avail. Instead of looking for specific implementations like net.op error, we can loop, calling unwrap to remove context until either we reach EADDER not avail or there's no error left. This loop is so common, though, that Go 1.13 defines a second function, errors.is, that repeatedly unwraps an error looking for a specific target. So we can replace the entire loop with a single call to errors.is. At that point, we probably wouldn't even define this function. It would be simpler to call errors.is directly at the call sites. Go 1.13 also introduces a function errors.as that unwraps until it finds a specific implementation type. If you want to write code that works with arbitrarily wrapped errors, errors.is and errors.as are the wrapper-aware versions of error equality checks and error type guards. Now, whether to make it possible to unwrap an error is an API decision, like whether to export a struct field is an API decision. Sometimes you want to expose that detail to calling code, and sometimes you don't. When you do, implement unwrap. And when you don't implement unwrap. Now, until now, thump.errorf has not exposed an underlying error formatted with %v to caller inspection. So on the slide, if err2 is returned to a caller, that caller has no way to access err1. And we preserve that property in Go 1.13. But we added a new printing verb, %w, that formats like %v. It requires an error as an argument, and it makes the result of thump.errorf's unwrap method return that original argument to %w. So on the slide, if err4 is returned to a caller, then the caller can use unwrap to retrieve err3. When we published the design draft for unwrap, we also published a design draft for an optional method for richer error printing, including stack frame information and support for localized translated errors. This one's not as simple as unwrap, and I won't go into the details. As we discussed the design with the Go community over the winter, we learned that the design wasn't simple enough, and it was too hard for individual error types to implement, and it didn't really help existing programs enough. And on balance, it just didn't simplify Go development. And as a result, we abandoned this part of the experiment. That was error values. Now I want to talk briefly about error syntax, another abandoned experiment. Here's some code from compress.lzwriter.go in the standard library. At a glance, this code is about half error checks, and my eyes glaze over when I read it. And we know that code that is tedious to write and tedious to read is easy to misread. It's making a good home for hard-to-find bugs. For example, one of these 3 error checks is not like the others, a fact that is easy to miss on a quick skim. If you were debugging this code, how long would it take you to notice that? At GopherCon last year, we presented a draft design for a new control flow construct marked by the keyword check. Check consumes the error result from a function call or expression. If the error is non-nil, the check returns that error. Otherwise, the check evaluates to the other results from the call. This version of the same code uses check, which removes some lines of code, and more importantly, highlights that the call to e.inc is allowed to return out of codes. Maybe most importantly, the design allowed defining error handler blocks to be run when later checks failed. This would let you write shared context-adding code just once, like in this snippet. In essence, check was a short way to write the if statement, and handle was like defer, but only for error return paths. In contrast to exceptions in other languages, this design retained Go's important property that every potential failing call was marked explicitly in the code, using check instead of nil. The big problem with this design was that handle overlapped too much and in confusing ways with defer. So in May, we posted a simplified design. We dropped handle in favor of just using defer. And to match a similar concept in other languages like Rust and Swift, we renamed check to try. So now the same code would look like this. We spent most of June discussing this proposal publicly on GitHub. The fundamental idea of check or try was to shorten the amount of syntax repeated at each error check, and in particular to remove the return statement from view. One interesting point raised during the public feedback discussion was that if there's no if statement and no return, there's nowhere to put a debugging print, there's nowhere to put a breakpoint, and there's no code to show as unexecuted in code coverage results. The missing return would simplify programs, but at the cost of making these other situations more complex. On balance, from this, as well as other considerations, it was not at all clear that the overall result would be simpler Go development. So we abandoned this experiment. All right, that's everything about error handling, which was one of the main focuses for the year. Let's talk about something a little less controversial, like generics. The second big topic we identified for Go 2 was some kind of way to write code with type parameters. This would enable writing generic data structures and also writing generic functions that work with any kind of slice or channel or map. We've been thinking about this topic since work on Go began, and we wrote and rejected our first concrete design for generics in 2010. We also wrote and rejected 3 more designs by the end of 2013. 4 abandoned experiments, but not failed experiments. We learned from them, like we learned from check and try. We learned that the path to Go 2 is not in that exact direction, and we noticed other directions that might be interesting to explore. But by 2013, we had decided we needed to focus on other things, and so we put the topic aside. Last year, we started exploring and experimenting again, and we presented a new design based on the idea of a contract at GopherCon last summer. We've continued to experiment and simplify, and we've been working with programming language theory experts to understand the design better. Overall, I'm hopeful that we're headed in a good direction toward a design that will simplify Go development. Even so, we might find that this design doesn't work either. We might have to abandon this experiment and adjust our path based on what we learned. We'll find out. If you're interested, Ian Taylor is going to present the latest generics design tomorrow morning. The third big topic we identified for Go 2 was dependency management. Dependency management has been in the experiment and simplify and ship cycle for almost as long as errors and generics. From the very start of the language design, it seemed clear to us that we needed some decentralized way to manage the space of imported package identifiers, like Java has reverse domain names. We made import paths string literals in order to simplify that problem, so that text like a domain name or a URL could just be text, not parsed as program syntax. And in 2010, we published a tool called Goinstall, which we called an experiment in package installation. It downloaded dependencies and stored them in your Go distribution tree in Go root. As we experimented with Goinstall, we learned that the Go distribution and the installed packages should be kept separate, so that it was possible to change to a new distribution without losing all your Go packages. So in 2011, we introduced GoPath, an environment variable that specified where to look for packages not found in the main Go distribution. Adding GoPath created more places for Go packages, but it simplified overall Go development by separating your Go distribution from your Go libraries. The Goinstall experiment intentionally left out an explicit concept of package versioning. Instead, Goinstall always downloaded the latest copy. We did this so we could focus on other design problems for package installation. Goinstall became GoGet as part of Go1, and when people asked about versions, we encouraged them to experiment by creating additional tools, and they did. And we encouraged package authors to provide their users with the same backwards compatibility we did for the Go1 libraries. This convention simplifies the overall experience of using a package by restricting what the authors can do. Don't make breaking API changes, give new functionality a new name, give a whole new package design a new import path. And people kept experimenting. One of the most interesting experiments was started by Gustavo Niemeyer. He created a Git redirector called gopackage.in, which provided different import paths for different API versions to help package authors follow the convention of giving a new package design a new import path. For example, the Go source code in the GitHub repository goYAML has different APIs in the v1 and v2 semantic version tags. The gopackage.in server provides these with different import paths, gopackage.in/YAML.v1 and .v2. This convention of providing backwards compatibility so that a newer version of a package can be used in place of an older version is what makes GoGet's very simple rule, always download the latest copy, work well even today. But in production contexts, you need to be more precise about dependencies to make builds reproducible. Many people experimented with what that should look like. And all of these tools use the model that you copy dependency packages into your own source code repository. The exact mechanisms they then use to make those packages available for import varied, but they were all more complex than it seemed they should be. So after a community-wide discussion, we adopted a proposal by Keith Rarick to add explicit support for referring to copy dependencies without GoPath tricks and other complexity. This was simplifying by reshaping. Like with add to list and append, these tools were already implementing the concept, but it was more awkward than it needed to be. So adding explicit support for vendor directories made these uses simpler overall. Shipping vendor directories in the Go command led to more experimentation with vendoring itself, and we realized that we had introduced a few problems. The most serious was that we lost package uniqueness. Before, during any given build, an import path might appear in lots of different packages, and all the imports referred to the same target. Now with vendoring, the same import path in different packages might refer to different vendored copies of the package, all of which would appear in the final resulting binary. At the time, we didn't have a name for this property, package uniqueness. It was just how the GoPath model worked. And we didn't completely appreciate it until it went away. There's a parallel here with check and try. In that case, we were relying on the visible return statement in ways we didn't appreciate until we considered removing it. When we added vendor directory support, there were many different tools for managing dependencies, and we thought that a clear agreement about the format and metadata in vendor directories would allow these tools to interoperate, the same way that agreeing about the format of Go programs enables interoperation between Go compiler, text editors, and tools like Go imports and Go rename. This turned out to be naively optimistic. The vendoring tools all differed in subtle ways, and interoperation would require them changing to agree about the semantics and likely breaking their users. So at GopherCon in 2016, we started an effort to define a single tool to manage dependencies. As part of that effort, we conducted surveys with lots of different users to understand what they needed, and a team started work on a new tool, which became DEP. DEP aimed to be able to replace all the existing dependency management tools. The goal was to simplify by reshaping all the existing tools into a single one, and it partly accomplished that. And DEP also restored package uniqueness for its users by having only one vendor directory at the top of the project tree. But DEP also introduced a serious problem that took us a while to fully appreciate. The problem was that DEP embraced a design choice from Glide to support and encourage incompatible changes to a given package without changing the import path. Now let me show you what I mean. Suppose you're building your program and you need a config file, so you reach for version 2 of the YAML library. Now suppose your program imports Kubernetes. It turns out Kubernetes uses YAML, and it uses version 1 of the same popular package. V1 and V2 have incompatible APIs, but they also have different import paths. So there's no ambiguity about what is meant by a particular import. Kubernetes gets V1, you get V2, everything works. DEP abandoned this model. Version 1 and version 2 of the YAML package would now have the same import path, producing a conflict. Using the same import path for two incompatible versions, combined with package uniqueness, makes it impossible to build this program that you could build before. It took us a while to understand this problem, because we've been applying the new API means new import path convention for so long without fully appreciating it. The DEP experiment helped us appreciate that convention better, and we gave it a name, the import compatibility rule. We took what worked well with the DEP experiment and what we learned about what didn't work well, and we experimented with a new design called Vigo. In Vigo, packages follow the import compatibility rule so that we can provide package uniqueness but still not break builds like the one we just saw. And this let us simplify other parts of the design as well. Besides restoring the import compatibility rule, another important part of the Vigo design was to give the concept of a group of packages a name, and to allow that grouping to be separated from source code repositories. That name is a module, and so now we refer to the system as Go modules. Go modules are integrated with the Go command, which avoids needing to copy around vendor directories at all. And with Go modules comes the end of Go path as a global namespace. Nearly all of the hard work of converting existing Go usage and tools to modules is caused by this change from moving away from Go path. The fundamental idea of Go path is that the Go path directory tree is the global source of truth for what versions are being used. And the versions being used don't change as you move around between directories. Per project, reproducible builds are in direct conflict with the global Go path model. When you're working in a checkout of project A, you get one set of versions, the same one other developers from project A are seeing as written in the go.mod file. And when you switch to the checkout of project B, you get that project's chosen versions, the same ones that the developers of project B are using. But these are likely different from project A, and so as you switch, things change. This is necessary. There can't be a single global Go path anymore. Most of the complexity of adopting modules arises directly from the loss of this one global Go path. Where's the source code for a package? Before, the answer depended only on your Go path environment variable, which most people rarely changed. Now the answer depends on what project you're working on, which may change often. And everything needs updating for this new convention. Most development tools use the go/build package to find and load Go source code. We've kept that package working, but the API did not anticipate modules, and the workarounds we added to avoid API changes are slower than we'd like. So we've published a replacement, golang.org/x/tools/go/packages. Developer tools should now use that instead. It supports both Go path and Go modules, and it's faster and easier to use. In a release or two, we may move it into the standard library, but for now, the version of xtools is stable and ready for use. One of the ways that modules simplify Go development is by separating the concept of a group of packages from the source control repository where they're stored. When we talk to Go users about dependencies, almost everyone using Go at their companies asked how to route Go-get package fetches through their own servers to better control what code can be used. And even open source developers were concerned about dependencies disappearing or changing unexpectedly and breaking their builds. Before modules, users had attempted complex solutions to these problems, including intercepting the version control commands that the Go command runs. The Go modules design makes it easy to introduce the idea of a proxy, a module proxy, that can be asked for a specific module version. And companies can now easily run their own proxy with custom rules about what's allowed and where to store cached copies. The open source Athens project has built just such a proxy. And to learn more about that, come back tomorrow for Aaron Schlesinger's talk in the morning. And for individual developers and open source teams, the Go team at Google has launched a proxy that serves as a public mirror of all open source Go packages. And Go 113 will use that mirror by default when in module mode. For more information about that, including why it's safe to use, you can come to Katie Hockman's talk here this afternoon. So Go 111 introduced modules as an experimental opt-in preview. We'll keep experimenting and simplifying. Go 112 shipped improvements, and Go 113 will ship more improvements. Modules are now at the point where we believe they will serve most users. But we aren't ready to shut down Go Path just yet. We'll keep experimenting, simplifying, and revising. The Go user community has built up almost a decade of experience and tooling and workflows around Go Path, and we recognize it will take a while to fully convert all of that. But again, we think that modules will now work very well for most users, and I encourage you to take a look when Go 113 is released. As one data point, the Kubernetes project has a fair number of dependencies, and they have migrated to using Go modules to manage them. So you probably can too. And if you can't, please let us know what's not working for you or what's too complex, and we'll experiment and simplify. Error handling, generics, dependency management are going to take a few more years at least, and we're going to focus on them for now. Error handling is close to done, modules will be next after that, and maybe generics after that. But suppose we look a couple years out to when we're done experimenting and simplifying and have shipped error handling and modules and generics. Then what? It's difficult to predict the future, but I think that once those three have shipped, that may mark the start of a new quiet period for major changes to the language. Our focus at that point will likely shift to simplifying Go development with improved tools. Some of that tool work is already underway, so I want to finish this talk by looking at that. As we helped update all the Go community's existing tools to understand modules, we noticed that having a lot of development helper tools that each do one small job is not serving users well. The individual tools are too hard to combine, too slow to invoke, and too different to use. So we began an effort to unify the most commonly required development helpers into a single tool, now called gopls. Gopls speaks the language server protocol, LSP, and it works with any integrated development environment or text editor with LSP support, which is essentially everything at this point. Gopls marks an expansion in focus for the Go project, from delivering standalone compiler-like command line tools like govet or go rename to delivering complete IDE service support. For more about Gopls and IDEs, I encourage you all to come back for Rebecca Stambler's talk later this morning. After Gopls, we also have some ideas for reviving GoFix in an extensible way, and also for making govet even more helpful. So there's the path to Go 2. We'll experiment and simplify, and experiment and simplify, and ship, and experiment and simplify, and do it all again. And it may look or even feel like the path goes around in circles, but each time we experiment and simplify, we learn a little bit more about what Go 2 should look like and move another step closer to it. Even abandoned experiments like try or our first 4 generics designs are not wasted time. They help us learn what needs to be simplified before we can ship. And in some cases, they help us better understand something we took for granted. And at some point, we will realize that we have experimented enough and simplified enough and shipped enough, and we'll have Go 2. So thanks to all of you in the Go community everywhere for helping us experiment and simplify and ship and find our way on this path. And thanks to everyone here in this room for traveling to San Diego today. And finally, putting this conference together is an enormous job, so thanks very much to the organizers for all their efforts. Enjoy the conference.